Just screen.
Good morning, Professor Rizwan Hasatan.
Good morning. Assalamualaikum. How are you?
I'm fine.
Waalaikumsalam. Alhamdulillah.
Waalaikumsalam.
Welcome, Professor. How are you?
Thank you. Thank you. Thank you. I cannot look your face. I'm just struggling with my computer. Let me find out. Can you see me?
Okay.
Bu Agus mungkin bisa open itu videonya.
Okay.
Biar lihat wajah Bu Agus.
Share.
Lagi masak ya?
Nice to see you again, Prof.
Yeah. Thank you. Thank you. Can you see the slide now?
Okay, yes,
yeah.
you can see it.
Okay. So how the things in Indonesia? What about the COVID situation?
Yeah, in some places we have flood, but yes, under control. Yeah, it's
Okay.
happen every year in the rainy season.
I see. I see.
Yes.
In India also, the situation is much better now. Alhamdulillah.
Alhamdulillah.
Yeah. So how many participants they were supposed to join this meeting?
Well, usually around 200, but most of them join in the after 5 or 10 minutes. Yeah, and yeah, because the rainy situation sometimes also disturb their signal. But
Okay.
yeah, usually around 200.
Okay. And regarding the participant, they are the students or they are the faculty members?
Both faculty
Both.
members and students.
But mostly they may be the student.
No, usually mostly from the faculty members.
I see.
So
So
because we share it in the faculty member from any university and the representative groups we have from all of the Indonesian in chemistry as a society.
I see. So in labs, they are open over there?
Sorry?
Labs, people they are coming?
Some of them, some. Yeah.
Some. Okay.
Yeah.
You cannot see my picture now. I think why it's like this?
The slide is, we can see the slide.
But what about the camera? Because I think my face, that is not coming over here.
Yeah, we cannot see your face.
So why it's like this? I just...
But it's fine because it's better than when presentation, all of the
participant
member, yeah, should turn off the video because usually disturb the PowerPoint.
Quality.
Yeah, the
Okay.
quality of the PowerPoint. Yeah. For now, because it hasn't start, we can. But when start, we usually ask the all of the to turn off their video.
Okay. So shall we start or shall we wait for?
Okay, I think we can start because the participant starting to add is around 50 now, and I think within 5-10 minutes, a lot of them will be joined. So I think I will start now. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Peace for us all. Good morning, everyone, ladies and gentlemen. Welcome to the program. I am Agustina. It is my pleasure to be a moderator for the JKSA webinar series on chemistry on how vitamin inhibits amyloid by Professor Dr. Rizwan Hassan Khan from Aligarh Muslim University, Aligarh, India. First of all, may I briefly introduce to you all our keynote speaker, Professor Rizwan Khan, graduate with a bachelor's, master, and doctoral degree in interdisciplinary biotechnology from Aligarh Muslim University, India. He gained his full professor since 2011. Some of visiting fellow, including University of Michigan, USA, University College of London, and 𝐸𝐴 University, Riyadh, Saudi Arabia. His interest research subject, including protein folding, protein misfolding, amyloids, protein aggregation, protein biochemistry that recently has a lot of attention from around biochemistry scientists. And he has a significant publication in Scopus. There are 327 papers with more than 11,000 citations, and the index Scopus of professor is 52. So it is an impressive scientific achievement. Well, without further ado, I would like to welcome Professor Rizwan Hassan Khan, our speaker, to deliver his presentation. So, Professor Rizwan Khan, the time is yours.
Okay, thank you, Augustina, for your kind words and a very nice introduction. So now I'll start my lecture. Today I'm going to speak on how vitamins is going to inhibit amyloid fibril formation. So let us start with the introduction part. So once the protein that is going to get synthesized on a ribosome, it's going to fold properly and it's going to perform a normal function. But in some cases, you may be getting the misfolding of the protein because of one or other reason. And in that case, there will be the loss of the function, and this may lead to the inborn error of the metabolism. In other cases, we get the overproduction.
Excuse me, Professor, can you make it the slide?
Slides are not visible?
No, the slide visible, but slide screen, yes.
Slide show.
To make it the bigger.
Bigger?
Yeah, slide screen, yes.
Is it okay?
Yeah.
Is it
Very
okay now?
nice. Okay. Yes,
okay.
Yes.
So in some cases, you may be getting the aggregation of the protein, and in that case, it is going to gain a toxicity, and this may lead to neurodegenerative disorder. In some cases, we get the mutation in the protein, and these misfolded or mutated protein, they are going to get recognized by the proteasome, and they are being degraded into peptides and free amino acids. Now, if you see the protein aggregation phenomena, they lead to a lot of diseases, especially neurodegenerative diseases like Alzheimer's, Parkinson's, and many others. So we were interested to find out what are the factors they are responsible for the aggregation of the protein. So the first question that we have asked, whether we take alpha class of protein or beta class of protein or random class of protein. So what is the substance that can be used to induce the amyloid fibril formation in all the different classes of the protein? So this is the question that we have raised, and this is the study that is being published in PLOS One in 2012. So here we have this slide is very important because here I am going to summarize what are the techniques that we are using in our lab. So relay scattering, this is a fluorescence based where we are supposed to excite at 350 nanometer and take the emission also at 350 nanometer. This is a highly sensitive technique to measure the aggregation of the protein. Another one is a spectrophotometric base. Here we are supposed to measure the absorbance at 350 nanometer or wherever we get a maximum lambda max. At that wavelength you can select and then you can monitor the rest of the points. The amyloid, they have a unique binding for the two dyes. One is the TST and another is the Congo red. So TST binding assay, this is a fluorescence based. Here the excitation is at 440 nanometer and emission at 485 nanometer. Another one is the Congo red. Here we are supposed to take the absorption spectra in the absence and in the presence of the Congo red between 400 to 700 nanometer. If we get a red shift, so that may be around 540 nanometers. So then we can say we are having the formation of the amyloid. CD measurements, these are being performed to characterize, because we know that amyloid, they are rich in cross beta sheet-like structure. So in that case, we are supposed to measure the CD spectra from 190 to 50 nanometer, and we'll be getting a negative peak that may be confined around 210 to 228 nanometer, which will indicate the formation of the beta structure. Further, seeing is believing. Unless you can see the structure, you cannot believe that. So here we are performing a 10 electron microscopy and in some cases fluorescence microscopy also. And so here you can characterize, see the morphology of the aggregates or the amyloid which are being formed. Now, this is very simple chemistry. Here we know that the proteins, they are made up of amino acids. And amino acids, they are of different types. Some they are positively charged, some they are negatively charged, some they are rich in hydrophobicity. So we are more interested in positive and negative. I will let you know why we are more interested. Positive amino acids are histidine, arginine, and lysine. And negative amino acids are aspartic acid and glutamic acid. If the protein is rich in overall positive charge, so then we can say this protein is basic in nature. Like histone protein, lysozyme, they are rich in basic amino acid residue, and it is because of that their isoelectric point, which is known as a pi, that is quite high. While there are some protein which are overall rich in the negative charge amino acid residue, they are known as a acidic protein like invertase. So now coming to this point that each protein, they have different number of positive and negative, and the overall charge of the protein, that is going to govern by the sum difference of the two. And each protein, they also have unique isoelectric point. Now here, if we are going below pi, isoelectric point means pi. So if we are going to below pi, so all the protein, if we are going below pi with respect to that protein, so in that case, the protein that will acquire a overall positive charge. So this thing is very important to understand the rest of the phenomena. And if we are going above pi of that particular protein, so in that case, the protein, it will be acquiring overall negative charge. Please mute your mic so that there shouldn't be any disturbance. So I can take one example. Say for instance, if the pi is around 5 of this protein that we are going to take, and if we are going to at pH 7, so in that case, the protein, it will acquire overall negative charge. And if we are going to at pH 3, so it will acquire a overall positive charge. So this is a simple chemistry you should keep in your mind to understand the coming slides. Now, here we have taken 25 different proteins. The first group that belongs to alpha class of protein, which include human cerebellum, porcine, bovine, sheep, rabbit, 𝐷, fatwin, esylofetwin, glucose oxidase, invertase, alpha-lactoglin, alpha-amylase, and conoglin. All these protein, they are rich in alpha content. So it is because of that they are called as alpha class of protein. The second group that we have taken, it's alpha plus beta. So here you will be having both the structure, they will be in almost same proportion. So, and the examples are lysozyme and hemoglobin. The third group that we have taken, it's all beta class of proteins, which include CON-A, cobratoxin, beta-lactoglobin, bovine liver catalase, chymopapin, tritagine, and lectin. So all these proteins, they are rich in beta structure. And one protein that is being taken, which is a random coil, and that is the gelatin. Now, we know that once the protein is going to get synthesized in the cell, it is going to come into a close contact to the plasma membrane. And the plasma membrane, it is made up of the phospholipids. Here is the structure of the phospholipid. You can see it is having a hydrophilic head and hydrophobic tail. So keeping this point in our mind, what we have decided that it's better to take something which is very similar to the phospholipid. So here we have taken a SDS, which is a negative charge. So here you get a negative charge, and in the SDS also we get a negative charge at group, 12 carbon long hydrophobic tail. CMC is around 8 millimole. Most important part is it is going to mimic the characteristic of biological plasma membrane. It is because of that we have taken the SDS. Now coming to the result part, my talk in this presentation that will focus on these techniques like Rayleigh scattering, turbidity, TST, CD, and TEM. And in this slide, I will talk about the control, while in the coming slide, I will just skip that so that I can save my time. So here we are monitoring the Rayleigh scattering, and each different proteins which belongs to different class, we have taken at 5 micromolar concentration at neutral buffer. Neutral buffer means at pH 7. We just want to see whether at pH 7 there is any Rayleigh scattering or aggregation phenomena that is taking place or not. So what we found that at pH 7, irrespective of the classes, none of the protein they were showing a positive Rayleigh scattering. The second combination that we have taken is 5 micromolar protein, 2 unit below pi. Now just keep this point in your mind. Once I am saying 2 unit below pi, so that means we are talking about a positively charged species. So even in that case also, we won't get any positive Rayleigh scattering because you cannot see any red over here. The third combination that we have taken is a 5 micromolar protein, 2 unit below pi, along with the 500 micromoles of the SDS. So here you can see all the protein, irrespective of the classes, they show a positive Rayleigh scattering. Now this is a very interesting phenomenon. So just to overrule, what we have done, we have taken the other side. That is, here in this case, we have gone 2 unit below pi. We just want to see what is going to get happen if we are going above pi. So here we have taken 5 micromolar protein, 2 unit above pi along with the SDS. So in that case, we are not getting any positive Rayleigh scattering. To conclude this slide, what we came to the conclusion that if we are going to take a protein which is 2 unit below pi along with the SDS, that is responsible for the positive Rayleigh scattering. Now, the second technique that we have used, it's a turbidity measurement. Here, I'll just skip, that's why I said, although we have taken the blanks and other things, but we are not showing it over here because just to save the time. So we got almost the same pattern as we got in the Rayleigh scattering in the previous data. Then the TST, as I said, the TST and Congo red, these are the two dye which are being used to characterize the amyloid. So here also you can see all the proteins which are being below pi along with the SDS, they show positive TST fluorescence. So this indicates that they are forming the amyloid fibrils. Now we are over here, CD data. Here you can see CD experiments that are being performed. So these proteins, they were being taken at neutral buffer. So if it is alpha helical protein, so you'll be getting a negative trough, one at 208, another at 222. This is a beta structure protein. This is an unordered structure protein. So if we are going to take all these protein at 2 unit below pi, so there was no significant change in the structure that was being observed. While if we take all this protein in the presence of the SDS, which is being 2 unit below pi also, so you can see all the protein irrespective of the classes, whether it's alpha class of protein, a random class of protein, alpha plus beta, all of them, they are going to adopt a beta rich structure. So this is going to get clear in this table. So here you just see the pointer. This is a pH 7.4, and here if you see, these are the protein that we have taken. The beta content that is being mentioned over here. Now, if we take 2 unit below pi, so in that case, there was no significant change in the beta content that is being observed. While the red one, this is being shown that the protein is 2 unit below pi along with the SDS. So here you can see that this is forming a, this is going to have a rich beta content. Now, these are the TEM images that are being shown. Now you can see that all the proteins which belongs to different class like alpha class, beta class, alpha plus beta, and random, all of them, they are showing a very clear-cut amyloid fibril formation in the TEM microscopy. Now, this is a summary of the work. Just to summarize this, please give the attention on this slide because this is very interesting. Now, as I said in the beginning, that we have a protein which may be having a different number of positive and different number of negative residues. They may be belonging to either of the class, like alpha class, beta class, alpha plus beta, or random coil. Now, this point is important. If we are going to 2 unit below pi, so you can see this is going to become a positively charged species. Protein is going to become overall positive charge. Now, if we are going to add the SDS, this is a schematic structure of the SDS that has been shown. This is the head and this is the tail. Head is having a negative sulfonate group. Now, this is going to interact with this and it's going to neutralize this charge, and this may facilitate the formation of the amyloid. While in this case, once we are going above 2 unit above pi, so in that case, the overall charge on the protein, it will be negative, and there will be a negative charge repulsion that will be there, and it is because of that we won't get any amyloid fibril formation. So from here we can conclude that SDS have a great potential to induce amyloid fibril formation when protein are subjected to 2 unit below pi. Both electrostatic as well as hydrophobic interactions are responsible for amyloid fibril formation. Now, from the first part, it is become clear that whether we take any class of protein, alpha plus beta, beta, random, or any type of protein, and only condition that is required is each protein, they will be having unique isoelectric point. We should go below that, and the protein that is going to acquire a positive charge, then we can add a anionic surfactant and we get the amyloid fibril formation. Now here, what we want to see, that we just want to fix the 2 parameters. We want to fix the protein, we want to fix the SDS. We are fixing the concentration of the protein as well as the SDS. To layman, we can say in that way. And by changing the pH, the protein is going to have more charge on that. So in that case, we want to see that, suppose this is schematic structure that is being shown. At 1 pH, it is having 8 positive charge, and at other pH, it is having 14 positive charge. So what we are speculating that if there is more positive charge, so in that case, there should be more amyloid fibril formation should take place. So here you can see there is only 1 bundle that is being shown, and here you can see there are the 3 bundles they are being shown. It's just a schematic. This is the hypothesis that we have given. Keeping in mind that the SDS and the protein concentration that we are taking, it's a fixed concentration. So this is a study that is being published in Soft Matter. Now, this is a protein that is being taken, hen egg white lysozyme. This is alpha beta class of protein. 129 amino acid residue, 9 are negatively charged, and 17 are positively charged residue. It's having the two domains, alpha domain and beta domain. Only point that is important for this discussion is the protein is having isoelectric point is around 11. Now this point you should keep in your mind, because only then you can understand the rest of the thing. Now coming to the result part. We know that the protein that we have selected, it's having isoelectric point around 11. So you just see at 11, the overall charge on the protein, it will be 0 because it's an isoelectric point. So there is a way by which you can calculate the charge by using a software which is known as a protein charge calculator 3.3. You can determine the charge at different pH. So here you can see we have determined the charge on the protein at different pH starting from 11 to 1. And you can see as we are lowering the charge, as we are lowering the pH, so we are getting more and more positive charge. You just remember two values, that at pH 9, it's having a approximately 5 positive charge, and at pH 1, it's almost having a 19 positive charge. So just you remember this figure, because in the conclusion, I'll again come to this point. Now here again we'll go by this. We perform a relay scattering turbidity, TST, Congo rate, CD, and TEM. So whenever we are going to perform a relay scattering, it's better to and you are changing the protein concentration. So you are supposed to find out what is the stoichiometry that is going to give the maximum turbidity. So here you see, since we are taking 15 micromolar concentration of the lysozyme, so we want to standardize the concentration of the SDS. What is the max concentration of the SDS? That is going to give a maximum relay scattering once we are going to use 15 micromolar concentration of the lysozyme. So here you can see this is the relay scattering graph that is being shown, and here the point that is coming, which is around 0.3 millimole, because here the concentration of the SDS that is being shown in 3 millimole. So in the rest of the experiment, you can see we are going to use the 300 micromoles concentration of the SDS for 15 micromolar of the lysozyme. Again, here we have taken a lysozyme at different pH as a control, and we have taken lysozyme along with the SDS, and this is the control of the buffer that is also being taken. Now relay scattering that is being observed. Now here you can see as we are lowering the pH, so you can see that there will be a more and more positive charge, and it is because of that we are getting a maximum relay scattering at pH 1. Sometimes we get artifacts, so it is better to confirm with the kinetics data. So here we have performed the kinetics, and you can see a very steep hyperbolic curve that we have noticed for the pH 1 along with the SDS, then pH 2, then 3, then 5, then 7, and you can see there was no change for pH 8 and 11. So this further confirms that as we are lowering the pH, so we are going to get a more and more amyloid fibril formation. Now here you can see that we are going to test the turbidity, and along with the same controls as I discussed previously, so I'll just skip that. So you just see the turbidity is also going to get increased with respect to the lowering of the pH, and it was found to be maximum at pH 1. Now TST fluorescence that is being observed. Now here you can, some person can ask the question, although what we were expecting that we should get a maximum TST fluorescence at pH 1, but this is not the case. The reason is at pH 1 and 2, because it's a very strong pH, so here the TST masses, they get disturbed, and it is because of that we are not getting a maximum TST binding at pH 1. because each dye, they are sensitive towards the pH also. Even the Congo red, this is the Congo red data that is being shown. Now you can see this is the in the absence of the Congo red, this is in the present. So you can see the spectra that is going to get shift towards the right hand side. If the spectra is going to shift towards the right hand side, this is known as a red shift. And this is an indicator that there is a amyloid fibril formation that is taking place. So here you can see only pH 7 and 5 data that is being shown, and rest of the data that is being shown in the tabular form. So in this case also you can see from 11 to 5 we have not gone below 5. The reason is this dye is also going to lose the color if you are going to go below pH 5. So here most interesting thing is, if you just see that this as we are lowering the pH, we are coming from 9 to 5, the extent of the red shift is going to get increased. There's a 10 nanometer red shift starting from 5 to 10. So this indicates that it is a strong propensity of the amyloid fibril formation. Now here we are showing some representative CD spectra at pH 1, 3, 5, and 7. So you can see this is a lysozyme. So this is alpha beta class of protein. And once if we are adding the SDS, so in that case, you can see it is going to adopt a beta sheet-like structure. Now these are the time images that are being shown. This is at pH 9, 6, 3, and 1. If you just see the D part, which is at pH 1, so you can see it is a very dense amyloid fibrils that are there. So this again further confirms that as we are going to lower the pH, we get a more amyloid fibril formation. Now again, I always enjoy to give a cartoonic presentation because this is going to imbibe in the mind. So here you can see this is the lysozyme which is being shown. It will be having a more number of positive than the negative, because as I told you in the beginning, that if the protein is basic in nature, so it should be rich in more positive residue. Now at pH 1, if you just recall, I said that it will be having 15 overall positive charge. And at pH 9, it will be having 5 overall positive charge. And it is because of that we have shown 5 plus 1, 2, 3, 4, and 5. One thing you just notice that the stoichiometry of protein to SDS is fixed in all the cases. 1:20.
हेलो
हेलो
अस्सलाम वालेकुम
वालेकुम
भाई इसका बताइए मस्जिद पहली वाली करी है ना मस्जिद पहली वाली
जी 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 आ जाइए ये भी 40
ये भी करी
okay, sorry for the disruption. So now you can see that at pH 1 it's having more positive charge as compared to pH 5. This is another story that I'll talk later on. So in all the cases, if you just see, this is having a fixed 1:20 stoichiometry of the protein to detergent. Now here you can see if the charge is less, so we get less amyloid fibril formation. If the charge is more, so we get more amyloid fibril formation. And if we are going above pi, so again in that case it will be a negatively charged species. And if we are going to add the SDS, so there will be the charge repulsion, and in that case we won't get the amyloid fibril formation. So from here we can conclude that the aggregation is observed to be maximum at pH 1 because of the maximum net positive charge on the lysozyme. SDS interact both electrostatically and hydrophobicity and lead to the formation of the amyloid. Now the third hypothesis, excuse me, what is the time limit? It is 1 hour. Time limit is
around 40 to 45.
40. So I'm supposed to skip some part.
Okay.
It's almost 30 minutes I have taken, no?
Yes.
So in 10 minutes I'm supposed to wind up.
You have already yes, 10 to 15 minutes.
Okay, so I'll just skip this part because Then, very quickly, I will go for this also. So here, what we have done, we have taken 5 different albumins, and then we have taken a detergent with varying chain length. So till now, what we have talked about, that in the first part, we have said that we take a different class of protein, and then by take only thing that is required, the protein should acquire a positive charge, and then we should add a counter ion, that is the SDS, and that case we get the formation of the amyloid. In the second part, we have shown that as the charge that is going to get increased, we get more formation of the amyloid. Till now, we didn't talk about the hydrophobic part. So here what we want to show, that I'll go very quickly because of the limitation of the time. So I cannot discuss the full results. So we have taken 3 detergent which differ in the chain length: SDS, SDBS, and AOT. SDS is 12 carbon, and SDBS is 18 carbon, and AOT is 20 carbon. And all of them, they have negative charge head group. This is a study that is being published in Physics, Chem Physics in 2014. So I said these were the albumin that were being taken. Only point that is important is we have taken 5 points. These all albumin, they have isoelectric point that is around 5.6. This is a structure. I will skip that, and then I will come to the result. Now, again, we have measured the Rayleigh scattering stability, TST, congruent, CD, and TEM. And here you can see it is the AOT which is showing a persistent, more positive Rayleigh scattering in all the different classes of the albumin, whether we talk about the kinetics, whether we talk about the turbidity, whether we talk about the TST, whether we talk about the congruent, whether we talk about the CD, whether we talk about the TEM also. So this is the TEM images that is being shown over here. Now you can see this is in the presence of the AOT. The upper panel is bovine serum albumin, human serum albumin, and the lower panel is bovine serum albumin. We have shown in the 2 proteins so that we should rule out that it's not an artifact. So AOT, which is having more hydrophobic chain length, so here we are getting the more amyloid fibril formation. So from here, what we can conclude that that if there is a hydrophobicity that is going to get increased. So this is schematic structure that is being shown. This is SDS, which is 12 carbon. This is 18, and this is 20. Now you can see as the carbon chain length that is going to get increased, so we get a more and more amyloid fibril formation. So what we can say, conclude with this, that hydrophobicity that also plays an important role. We cannot overrule that. So more the hydrophobicity, more the amyloid fibril formation. But the first and most important thing is the charge neutralization. So there should be charge neutralization followed by the hydrophobic interaction. Now, there may be the question that may come to your mind, why I'm so much biased to the positively charged protein. And in that case, I'm using the negatively charged surfactant. So just to take the another part also, so we have taken a lysozyme. Lysozyme is a very good protein because it's having an isoelectric point around 11. So if we take the protein at pH 9 and 13, at pH 9, the protein, it will be positive charge, and at pH 13, it will be a negatively charged. So for a positively charged protein, we are using the 2 surfactant, SDS and AOT, which are anionic in detergent. And for the negatively charged species, we are using cationic. The overall, what we can summarize, that we just want to neutralize the charge. If the charge on the protein is positive, we are going to take anionic detergent. If the charge on the overall protein is negative, we are supposed to take a cationic detergent. In a nutshell, we can say it like that. I will skip this. So SDS and AOT, the structure that is being shown, this is anionic. They differ in the chain length. This is very important. 12 and 20, and this is also going to influence. This is 12 and 16. Now we'll come to the result part. So again, it's a turbidity measurement that is being shown in the upper panel at pH 9 and at pH 13. So we get the order like this: AOT, CTAP, SDS, and DTAP. Because of the limitation of the time, I'm not going to discuss the result in detail. Similar pattern is being observed for the relay scattering, then that dye banding, Congo red, and ITC. So this is very important data, because from here you can see the enthalpy, the first enthalpy for all the detergent that is coming to be negative. So this proves that it's favoring the hydrophobic interaction, and the second enthalpy that is coming to be positive. So that proves that it's there is a hydrophobic interaction that is taking place, and the overall order that is being governed by the chain length. So AOT followed by CTAB, SDS, and DTAB. AOT, as I said, is 20, 16, and 12 carbon chain length. Now these are the AFM. This is another type of microscopy. TEM I already discussed, and fluorescence. So you can see there is if there is more chain length, so we get more for amyloid formation. This is AOT followed by CTAB, SDS, and DTAB. Now this is a schematic presentation. Now again, now as I said, it's a lysozyme. If we are going to pH 9, it will be positive charge. Here we are supposed to use anionic surfactant, and then we get the amyloid. And if it is a negative charge species, so we are supposed to use a cationic. Now this positive charge is going to neutralize this negative, and this may facilitate the formation of the amyloid. If we are going to replace this cationic with the anionic over here, so in that case there will be a charge repulsion. There won't be formation of the amyloid. That we have already shown in our previous slides. Now we are going to come to the therapeutic approach, because we know that people, they generally suffer from the Alzheimer, Parkinson's, and many diseases. So what should be the cure for that? So this is a very important question, and how come we can address that? So there are the different approaches that are being used. One is the inhibition of the protein aggregation by small molecules which interact with. Hello? Is there any question?
No.
Hello?
No. Yes?
Any question?
No. It's
So if we can inhibit the aggregation by taking a small molecule. Please mute your mic so that I can continue within a time. Another one approach is that is the selective inhibition by RNA interference, and the third approach is upregulation of molecular chaperones for the clearance of the aggregates. Now, in our lab, we are working on the inhibition by the small molecules. We are taking some natural compound. So it is always better to go close more towards the nature. And you can find out what are the things that the nature has provided or the God has provided. You can use those substances and they will be having a lot of beneficial effects, like black seed oil and so many other things, vitamins and so many 𝐬𝐻𝐼𝐸 and other products. So what we have checked that we have seen the effect of vitamin A, B, C, K, taurine, 𝐬𝐻𝐼𝐸, and many others. And we have also tested the already drugs that are available in the market, especially the anti-tuberculosis drug, because in India and other undeveloped countries, people, they suffer from the even in developed countries also, it is being reported that people, they suffer from the tuberculosis. So we have also tested the anti-tuberculosis drug, how they are going to prevent the amyloid fibril formation. So here we are going to discuss about the role of the vitamin A. So this is the A beta, which is responsible for the Alzheimer's disease, A beta 42. So what we have done, we have taken in the presence of the varying concentration of the vitamin A. So now this is the tasty fluorescence that is being shown. Now you can see at 100 and 200 micromoles, there is a steep decrease in the kinetics that is taking place. This is the CD data, which is also going to confirm the same. And this is the DLS data. You can see this is at room temperature. This is the aggregate that is being formed. And this is in the presence of 100 and 200 micromoles of the vitamin A. So you can see the hydrodynamic radii that is going to get decreased, which further prove that these vitamins, they show a inhibitory effect. Then we perform a transmission electron microscopy also. This is the control where we get the amyloid, and this is in the presence of the 100 micromoles of the vitamin A, and this is in the 200. So you can see there is a less amyloid fibrils, they are being reported over here. The cell viability assay that is being performed by using the MTT assay on the SHSY5Y cell line. So here you can see this is the control where the cell viability is 100%. If you are going to take a beta peptide, which is the going to form the amyloid, cell viability that is going to go down. So here upon the addition of the 100 and 200 micromoles of the vitamin A, you can see there is a restoration of the viability that is taking place. Now, this is the molecular docking. Again, we can conclude that vitamin A show a inhibitory effect. Now, vitamin B12 is being shown over here. Because of the limitation of the time, I'll just go very quickly. And this is the A beta again, it is being taken, and you can see 25 and 50 micromoles of the vitamin B12. They show a pronounced inhibitory effect, and this is the data from the here that is being representative tasty fluorescence data that is being shown over here. Now this is a congruent. Again, it shows the inhibition in the presence of 20. This is 25 and this is 50 micromoles of the vitamin B12. This one, and this is the congruent alone. So you can see it is approaching towards the free congruent. So this confirms that it is showing a inhibitory effect. Now this is ANS binding. If there is a less hydrophobic patches, so that shows a inhibitory effect. So here you can see in the presence of the 50 micromoles of the vitamin B12, there is a less ANS binding that is taking place. This is the hydrophobic dye. This is CD data. This is the TEM image. Again, you can see this is the control, and this is in the presence of the 100 micromoles of the vitamin 25 and 100 micromoles of the vitamin B12, which shows a pronounced inhibitory effect. Now the third vitamin that we have taken is vitamin C. This is a study that is being published in PLOS One. This acts as also a cofactor, and here the protein that's being taken as a human insulin. I'm just skipping the details of these data because of the limitation of the time. So here you can see it is 200 and 400 micromoles of the vitamin A. They show a pronounced inhibitory effect, and this is the fluorescence emission spectra of these points. They are being depicted over here, which further confirm that this is having strong inhibitory effect. This is the ANS fluorescence data. Now this is the human insulin, because it's a human insulin which is being incubated at 60 degrees centigrade for 72 hours. So it's going to have a capacity to bind to ANS, and it is because of that it's being shown over here. So this, and ANS blank is over here. Now in the presence of 200 and 400 micromoles of the ascorbic acid, you can see it is approaching towards the free ANS. So this confirms that it's having a inhibitory effect. Now this is the CD data. Here you can see the ellipticity that goes down, that is going to get decreased in the presence of the 200 and 400 micromoles of the ascorbic acid. This is at a room temperature. So we are not more interested in this one. We are more interested in this data. So you can see that ellipticity that's going to get decreased in the presence of the 200 and 400 micromoles of the ascorbic acid. So this confirms that it's having an inhibitive potential. Now this is the control. At 25, we won't get any amyloid fibril formation. This is which is being incubated at elevated temperature for a particular time. Here we get amyloid, and this is along with 200 and 400 micromoles of the ascorbic acid where we get the inhibition. This is MTT assay that is being performed, molecular docking. I'll just skip that. Now this data is very interesting. I'll just like to get a focus of the audience on this. See, there are the two phases. One is the person is undergoing the disease. Say for instance, it's an Alzheimer's disease. Some person is going to, initially, he's not going to realize that he is suffering from the Alzheimer. So it is going to take a time. So if that person is going to take vitamins, so within a required amount, especially what I will say, the water soluble, B and C, because if you are going to take an excess amount of fat soluble, so that may be having some complication. But water soluble vitamin, they will be excreted out. It's not a big issue. So here what we have shown, and the other case is the person has already suffered the Alzheimer or Parkinson disease. Now what should be the strategy? Because the aggregates, they are already being formed. Now we want to disaggregate all this. Whatever the aggregates they are being formed, the cluster that is being formed, we want to disintegrate. So here what we have shown that this is the control, and we have here, this is the preformed fibrils, and they were being kept for the different time interval. And here the red one, which is being taken with the 400 micromoles of the ascorbic acid. Now you can see, even if the preformed fibrils, this is the preformed fibrils, and if you are adding the 400 micromoles of the ascorbic acid, so it is going to show the inhibitory effect. That means they are going to disaggregate all the preformed amyloid fibrils. So this is very interesting approach. And this is also being proved by the cell viability assay also. Now I'll skip this and I'll come to the last one. That is, here we have taken the, vitamin K. So in vitamin K, this is the study that's being published in scientific report, which is of Nature group. And here we have taken two protein, lysozyme and A-beta, which were being incubated at the desired pH and desired temperature for a particular time period in the presence and absence of the vitamin K3, vitamin K3. So you can see, and this is the TST fluorescence, and you can see at 50 micromoles, there is a inflection point that is taking place, and at 100, it's become almost saturated. So then we have selected this 50 and 100, and we perform a kinetics. You can see the steepness of this curve is going to get decreased significantly in the presence of the 100 micromoles of the vitamin K3. This is the TST fluorescence data. This is a congruent. Again, you can see this is in the presence of 50 and 100 micromoles, and this is a free congruent. So it is approaching toward the free congruent. So this indicates that it is showing a inhibitory effect. Now this is the kinetics that is being performed with the A-beta in the presence of 50 and 100 micromoles of the vitamin K3, which further prove that it shows a inhibitory effect. Now this is CD data, DLS data. Now DLS data, you can see this is at 25 degrees centigrade. That means we are not inducing any amyloid fibril formation. Here we just want to see if we are going to add at room temperature, if we are going to add 50 and 100 micromoles of the vitamin K3, whether it's going to change the hydrodynamic radii of the protein. So it is not going to change the hydrodynamic radii of the protein. And here you can see once the protein is being incubated, so hydrodynamic radii is going to get increased. Increase in the hydrodynamic radii means it's forming a aggregate. Now, upon the addition of the 50 and 100 micromoles, you can see there is a disaggregation that is taking place. So it's showing a inhibitory effect in the present. So this is the MTT assay that is being performed. This is the TEM images. You can see this is the control. This is a fibril. This is in the presence of 50 and 100 micromoles of the vitamin K3. So which proves that there is an inhibition that is taking place. Previous one was with the lysozyme, and this one is the A-beta. So here also you can see that there is a inhibition that is taking place. So from here we can conclude vitamin K3 inhibits the aggregation of hen egg white lysozyme as well as A-beta 42. Vitamin K3 reduce the cytotoxicity. This study may help us to design a rational molecule for the treatment of amyloid associated diseases. This is our achievement, we have published more than 400 publication. This is not updated one. We have got a research grant from 13 different funding agencies. We have received 13 awards from different agencies. I have supervised more than 23 PhDs. And right now, 8 PhD students, they are working, and several postdoc people, they are also working in my lab. I'm having a research and teaching experience of around more than 20 years. And total citation is around 12,000. And I'm an editor of several journals like IJBM, Current Protein Peptide Science, Protein Peptide Letters, and many others. I had been to University of Michigan and University College London. I'm a Bentham ambassador also. Lastly, I would like to thank DBT, DST, UGC, CSR, and ASIMR for the financial support. And the work presented over here is being basically done by Dr. Javed Masood, who is presently a faculty in the Middle East. And another part, the vitamin-related part, that is being done by Dr. Parvez Alam. He is also right now in Denmark. He's doing a postdoc. Recently, he got a very good offer in the USA. And what will be my request, that I'll be happy to become an adjunct professor if somebody is going to invite me in that way, so that I can come to your place and have some research collaboration. And if somebody is interested to have a collaboration, he or she can write to me directly, and some part that maybe get done in Indonesia, and some part can be get done in India. And in that way, we can get more number of publication and some good quality journal. And if I'm going to become an adjunct professor in some university, so that is going to open the era, so that I can come to your place yearly and give a talk and interact with the students. So that is going to benefit to the students also with my experience. So it is your choice, whatsoever you feel better. And with this, I would like to thank for your attention. Thank you very much.
Thank you very much, Professor Rizwan Khan. Is very interesting subject. However, in Indonesia, the study in biophysics, especially in protein, is very limited. And your offer to teach us in Indonesia is very welcome, and we are very pleased to hear this, and we will see later. Since most of the participants here, some of them from the physical chemistry and do not really understand about the protein, so I would like to give a brief summary in bahasa about what you present. Just a little. Baik, Bapak Ibu. Jadi yang tadi disampaikan ini beliau adalah terkait dengan apa namanya penyakit Alzheimer gitu ya, dan bahwa penyakit degeneratif artinya penurunan fungsi dari sel itu adalah karena adanya kerusakan protein. Nah, protein yang rusak di sini adalah maksudnya terjadi perubahan struktur yang di sini disebut sebagai dalam bentuk amyloid. Amyloid itu adalah bentuk protein yang mengalami agregasi. Nah, sebagai model tadi di awal, biasanya agregasi ini bisa dibuat dengan cara pemanasan atau dengan chemical. Nah, yang dipaparkan di awal tadi adalah pendekatan baru bagaimana membuat model agregasi menggunakan deterjen. Tadi disampaikan beberapa deterjen. Nah, sehingga nanti dan yang terakhir sesuai dengan judulnya adalah bagaimana melihat efek atau mekanisme vitamin di dalam mengatasi terbentuknya agregasi ini. Nah, tadi sudah disampaikan bahwa ada peran positif dari beberapa vitamin di dalam mencegah terjadinya amyloid. Nah, ini sudah menjadi potensi untuk menjadi alternatif bagi pencegahan atau mungkin juga treatment dari penyakit-penyakit termasuk yang sangat berbahaya, yaitu tadi Alzheimer. Ya. Jadi itu mungkin yang bisa saya berikan secara singkat. Well, some of the participants already giving a question and some in Bahasa Indonesia, and I would like to translate. But the first question.
Bu Agustin, saya mau share itu, permisi, share pertanyaan sudah saya masukkan ke Mentimeter, jadi mungkin
silakan aja.
Rizwan untuk bisa
the question will be shared in the in this
screen,
so the professor can read also.
Yeah. So Professor Rizwan, could you please close your presentation in this screen? Because I would like to share something.
Tapi Bu Yayu, sebaiknya saya tanya apa Bu Yayu? I think let me just tell, because if close, Professor Rizwan would be have a problem to explain. So I think it would be better if just
if somebody can read the question, so then I'll be happy to answer that, because if I'm going to close this, I am going to exit from
meeting. So I will read some of the question. The first one is she asked about how do body protein experience. Yeah, I think it's not related to this to the subject, but maybe in the first part you tell a little bit about the genetic blood, and this come the question. So how do body protein experience genetic blood? Are blood classes that different from the result of organism cross can be categorized? Is it necessary to?
What I get from the question, that means a person wants to know that regarding the blood, like we have different blood groups also. So the reason is it is on the surface black group protein we get a difference. Rest of those things that are almost same, but see, even if we consider a blood group A, B, and O, so although it is we have the same RBCs, but only thing is at the terminal end they differ in the sugar moiety, and it is because of that we get the difference in the classification also, and we get a different types of blood group also.
Okay, thank you very much. So I think for the next question, it is in Bahasa. I would like to translate. Okay, this is a translation. What is the function of the SDS? So I think because the previous presentation is rather quick, so it needs to explain again.
This is good. I can explain that. See, only thing is, you know that start in this way. If there is a positive charge and there is another negative charge, that can neutralize or they can attract each other, and if there is a same charge, they will repel each other. It is the same principle that is going to get applied over here. And the two species, one is the protein and another is the detergent. So if you are going to provide a protein with a positive charge under some defined condition, like lowering the pH below their pI, so it will be having a positive charge, and in that case, if you are going to use a anionic detergent, which is a negatively charged, so there will be the charge neutralization, and that will facilitate the amyloid fibril formation. And the other side is, if you take a above pI, so the protein, it will be negatively charged. So in that case, you are supposed to take a cationic detergent. So it's a very simple chemistry. That's all. So that's why it doesn't mean whatsoever the branch that we are, the lecture that I'm going to present over here, it's a interdisciplinary. There is a role of the zoology, there is a role of the botany, there is a role of chemistry also, physical chemistry also can, like organic chemistry, inorganic also. Inorganic, you can synthesize a salt and then we can check whether they are going to inhibit the aggregation or not. Ionic liquids are there, so most of the people, they are looking for the ionic liquids also. So we cannot exclude that one branch that is totally unrelated. So it is all interrelated. So even chemistry people, they are going to get best fit in this branch because they can design some small molecule and we can check the inhibition of that molecule. Next question.
Thank you. Next.
What causes the decrease in the total charge when the pH increases? What causes the decrease in total charge when the pH increases? So I'll put in another way because it looks to be very confusing statement. First thing you should make in mind that each protein, just each individual, they have their unique name and unique fingerprint. It is on that basis, on the basis of the face, on the basis of the color, you can recognize that person. Likewise, each protein, they have a unique isoelectric point. This point you should keep in your mind. And this isoelectric point is nothing. It is on the basis of the total positive and negative charge. This part should be get clear. Now, if the overall charge on the protein is positive, so it will be basic, and most likely it will be having an isoelectric point above pH 7. Now, say for instance, if there is you are taking at pH, PI is a 7.5, and then if you are going to pH 5, so that means we are going below PI. So in that case, the protein is going to acquire a positive charge. Or on the other side, if we are going above PI, so in that case, the protein is going to acquire a overall negative charge. So as we are going above the PI, far away from the PI, so negative, and as we are going to just below PI, so it will be positive. Next question. What is the mechanism of vitamin on inhibiting the misfolding of amyloids? How it compares? This is a good question. I appreciate this. See, generally, if you see, once the protein they are going to get form, it is a hydrophobic core that is there, and that is supposed to be form a core-like structure, and then the charge residue they will be on the surface. So generally, it is being found that whether the chevrons or chevrons, what chevrons do, once the protein is going to get synthesized, the misfolded protein, they enter into chevrons and they are being correctly folded. And so here also, if there is a hydrophobic molecules are there, which are going to prevent the pi-pi interaction, so they are going to, most likely they are going to inhibit the amyloid fibril formation. And it is because of that we have taken a vitamin, and even we have shown the same phenomena with the anti-tuberculosis drug also. Next question. Sorry. Is the mechanism of inhibition of amyloid formation with vitamin is still relevant in such? Yes, of course, very much. Very, very much it's relevant, because only thing is that is required that it should be further get confirmed in the animal model also. That's all. Although we have performed and it is being published in very reputed journal, so there is no doubt about that. It is showing it, and it is, there are the several papers on vitamin D, because we haven't checked the vitamin D, because other group they have also tested the vitamin D, and they have shown a very similar result that we have got. So it is not one lab. Our lab have shown one aspect, and the another lab they have also shown that vitamin D also they have a pronounced inhibitory effect. So yes, it is very much relevant. Next question. How to count the number of positive or negative charge in amyloid? No, in amyloid, I think you are confused. It is what I have said. It is the protein we can calculate, because once you know, because you know that whatsoever the protein that you are handling, you know the number of amino acid residue. You just feed the number of amino acid residue primary sequence in a software, and then you can calculate the charge by the charge calculator at different pH. That's all. Thank you. Next one. What is the turbidity measurement Why is the turbidity measurement done at wavelength? Yes, this is because even if you might have noticed that I said it is not necessary 350. You take any sample. Suppose you are taking with a lysozyme bacterial extract or something like that. So the very first rule of the spectroscopy is you just find out the lambda max. Wherever you get the lambda max, at that particular wavelength, you are supposed to measure the rest of the observation. This is very relevant question that you have asked. So it is, I'm not saying it is in our system, we have noticed that we get a maximum turbidity at 350 nanometer for that particular system, for that particular protein. So suppose you are dealing with some other substance. For instance, I can say you are dealing with some plant extract or chlorophyll extract or animal hemoglobin, something like that. So in that case, make a solution, scan the sample, and wherever you get a maximum turbidity at that particular wavelength, you can measure the rest of the observation. It's a good question. Thank you. Any other question? You can get down, you can note down my email ID, rizwanhkhan1@gmail.com. If somebody is interested for the collaboration or something like that, so you are most welcome at any time. We can have a discussion, and if you want to submit, we are also editor in several journals also. So you can discuss how you can improve your manuscript also. So we can give you the input in what way you can write a better manuscript. So there are the different ways that we can collaborate. So that's why I said if somehow if I'm going to get an offer of the adjunct professor, so that is going to open a door. And it doesn't mean that only one department, all the department like chemistry, zoology, botany, biochemistry, and from the other university also people, they can come, and then we can have a 2 or 3 days meeting, and we can discuss the problems. We can discuss some collaborative work also, and in that we can progress. That is my idea.
Okay, thank you very much, Professor. It is another question or the new question?
Have you tried to analyze amyloid using cryo-EM? No, it's also a very good question, because cryo-EM is a recent technology. Although some people, they are using that, but we don't have these facilities. If somebody is having in the Indonesia, so I'll be happy to make that person collaborative person in my work, and he will be getting the name in my publications also. So I'll be happy if somebody can do the cryo-EM. We can send the sample, and his team can also get an authorship in the publication.
Thank you very much. There is another question still. The last. Okay. Yeah, I think the time, but I have one question, Professor. In the previous, you tell about the SDS as to make amyloid, but in the last presenting about the vitamin, the amyloid made by the high temperature.
Made by?
High temperature. It is at 60, 65. Because I wonder, and at the first that maybe the inhibition of amyloid using the SDS to make amyloid and then add with the vitamin. It is not?
No. That's a different part. The first part I discuss about what are the conditions that are being used to induce the amyloid. Then we have closed that chapter. Then it is not a SDS alone. In some cases, you can simply heat the protein at particular temperature and incubate it. So in that case, we get the formation of amyloid. So we are not adding the SDS in that. And then we are adding the vitamins. So SDS is not being added to that system.
Okay. Yeah. Yes, because what I learned from your previous presentation is I'm using the temperature to make the aggregation, and then when you introduce the SDS, I wonder whether is it possible to study the inhibition using the vitamin or the other compound and using the SDS for the aggregation?
No, it's better to make a system simple, because if you are going to use a multiple component, so then it will be very complicated story that will be there. So, so that is going to make a lot of confusion, and that paper is not going to get accepted easily.
I see. Okay. Yeah. Thank you very much for the explanation. I think. Oh, there are still one new question.
Yes, I'll be happy to answer. Can you explain briefly how is the principal mechanism of vitamin is in inhibiting the amyloid generation or amyloid formation? It's the same thing. So if you just recall what I'm saying, that take any protein and keep it at a high temperature for a particular time. So what temperature is going to do? Temperature is going to opening the structure of the protein. And once there is the opening of the structure of the protein that takes place, so there are the hydrophobic amino acids, they are going to come, they are going to get exposed. Now these hydrophobic patches, they are going to attract each other, and this is going to facilitate the formation of the amyloid. Now regarding the vitamins, if somehow you can prevent the hydrophobic interaction, so in that case you can inhibit the amyloid fibril formation. So generally, if you see the benzene ring or some hydrophobic moiety, if the vitamins, if they have some hydrophobic moiety, like in SDS we have the hydrophobic moiety, in the vitamin A also we have a hydrophobic moiety, in other vitamins also we have hydrophobic moiety. So to a layman, what we can say, it is a hydrophobic moiety that is being disrupted, and it is because of that we are not getting the formation of the amyloid. Still, if some people they have the doubts, so you can write me on my email. I can give a detailed answer on that, because sometimes people they are shy to ask the question in the conference. So feel free. I'm just like your brother, so feel free. You can ask me, drop an email, and if you have some problems related to your research, so whatever my experience is there, so I'll try to help you out. Inshallah.
Well, yes, thank you very much, Professor. I think the time is already finished, and I see another question, and the professor invite us to ask anything to the professor through his email, and also for the some participant that having problem join because of the rain and there is no electricity. We have already prepared this webinar in YouTube, and so the participant that cannot join today can watch in YouTube version. So thank you very much to Professor Rizwan Khan for his time and his valuable presentation. It is
thank you very much, Dr. Rizwan.
Take photo, Bu.
Oh, okay. Please, the participant to open the video. We are going to have a photo together.
Oh, baik. Oh, berarti nggak tapi bajunya. Kenapa nggak tidak dong?
2% lagi gimana?
Oke. Ready?
Bentar ya. Oke, belum. Ya. Ini akan ada 3 slide ya, Bapak Ibu. Jadi 3 kali fotonya ya.
Oke. the photo will be taken 3 times because of a lot of the participant.
Oke. 1, start. 2, 3.
Okay, finish, Bu Yayu?
Finish. Ya, terima
Okay,
kasih.
thank you very much, Bu Yayu, for the today. And again, thank you very much, Professor 𝐕𝐻𝑤𝑎𝑛 for this very valuable information. And he already invite us all the students and colleges to us and to make the collaboration in writing and everything that Professor already told us before.
So, if there is any way that we can submit a joint proposal, including 2 or 3 people, those who are doing a good science in different university, so that we can design some problem and then we can apply for some funds that maybe get from some of your funding agency, and in that way we can do some good quality research work also. Is this possible?
Yes, yes, of course, it is very possible for this, and I think all of us already hear about this offer, and it's common to make this kind of collaboration. And yeah, maybe because of this the subject, Professor, that I told previously, that in Indonesia the biophysical study, especially in protein, is just start. So, but from my previous experience, the technique that used Professor 𝐕𝐻𝑤𝑎𝑛 group, it is can apply by Indonesian comparing to another technique that applied from the another country. So I think a big chance for us to learn more, because the equipment and the technique available in Indonesia, but we still have a gap in the understanding about the structure of the protein most of the cases in Indonesia. But it is our chance to learn from the expert, especially Professor 𝐕𝐻𝑤𝑎𝑛 has already very kind to offer us for study, for collaboration. So it's a big opportunity for us. So thank you very much again to Professor 𝐕𝐻𝑤𝑎𝑛 for the presentation, and as well as for the offer for the collaboration. And I think we can make another kind of meeting in this form, but for talking about the collaboration.
Sure.
Yes. Okay. Well, thank you very much for all of the participants that join in this webinar, and I hope that we can meet again in another series of the JKSA webinar that will be performed in another month. Thank you, and I will close this this event. Wassalamualaikum warahmatullahi wabarakatuh.
Okay, assalamualaikum to everyone. All the best.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Professor 𝐕𝐻𝑤𝑎𝑛.
Thank you. Thank you. All the best.
Thank you.
Thank you.
Ya, terima kasih Bapak Ibu semua untuk partisipasinya.
Ya, nanti apa namanya informasi YouTube-nya?
Ya,
nanti bisa di-share ya di grup ya. Nanti saya akan share lagi di grup bagi yang belum sempat mengikuti, dan nanti sekaligus kita akan sampaikan apa informasi emailnya beliau gitu kan. Jadi bisa mudah untuk melakukan komunikasi selanjutnya jika tadi ada pertanyaan-pertanyaan yang belum tersampaikan. Oke, terima kasih semuanya.
Terima kasih. Selamat siang semuanya. Masih pada on.
Rekamannya masuk mana ya, Bu?